Now we want to spend some time talking about induced seismicity. Now that you have a fairly good understanding or perspective, at least, on the scale of seismic events that are produced in response to hydraulic fracture stimulation, they're usually, almost always events of a scale that aren't felt. Induced seismicity, on the other hand, represents events that are above, they don't fall in that negative range. They're usually above 0, and they're often felt, so that means they're above a magnitude 2.5 very often, not always, and can get as high as 5.8, as the recent one in Oklahoma, or a year ago or so, September of 2016. So we're going to talk about this in two parts. One, the induced seismicity associated with saltwater or wastewater disposal, and another possible source which most people are concerned about, which would be hydraulic fracture stimulation. This group of known induced seismic events associated with HFS is very small. So let's take a look at this. This is the induced seismicity. Can be produced by saltwater disposal, of course, but it can also be produced by other activities, impoundment of reservoirs. Build a dam. As the dam fills, you're changing the stress in the crust. You can produce earthquakes, surface and underground mining. You're withdrawing mass, changing the stress that way by reducing the overburden stress. Withdrawal of fluids and gas, same effect. Injection of fluids, again, you're loading here. And geothermal energy extraction, you're injecting fluids and withdrawing fluids, but the temperature difference is leading to contraction and fracturing of the rock, and then this hydraulic fracture stimulation. A good reference to take a look at here would be Ellsworth's 2013 paper. So, of course, the main issue with induced seismicity, if you're engaged in the development of unconventional resources, is you just don't want them to happen, because it's going to be a problem. The local communities in particular just are not going to want to have anything to do with it. So this is the kind of activity where you want to avoid at all possible costs producing these larger magnitude earthquakes, because it's just going to be a problem. Everybody knows that. That's not what people want to happen. So if we take a look at what's been going on in the eastern United States, and in particular kind of focus on this area in Oklahoma, it's worth pointing out that the U.S. Geological Survey came out with their first one-year seismic hazard forecast for the central and eastern United States from induced and natural earthquakes. So the first time that they've ever included this category in their hazard assessment. So if we take a look at that Oklahoma area, you can see that back in about 2009, we began to get an uptick in the frequency and the number of earthquakes with a magnitude greater than or equal to 2.7. So these are large earthquakes. These are the kinds of earthquakes that you might feel. This would be for the Oklahoma-Kansas area, which we are going to take a look at. And it's by far the largest. Contributes the greatest number of seismic events to this overall curve. So again, a good publication to reference there. This shows recent activity from a paper that was published in 2017, covering the period of 2013, 14, and 15, and 16, showing the activity in the Oklahoma-Kansas area. So definitely a lot of very, very significant. We're talking about numbers of events in the 4,000 per year up here in 2015, dropping off to about 2,500 here in 2016. So certainly a major concern for these people. This is the location of Oklahoma. You can see that this this earthquake zone extends up into the southern part of Kansas. This is just a comparison of the U.S. Geological Survey forecast from 2016 to 2017, and the chance of damage from an earthquake at 10 to 12%, 5 to 10%, and so on. Really, in my mind, there hasn't been too much change between 2016 and 2017, although several wells were shut in 2017, in late 2016 in response to the September 2016 magnitude 5.8 earthquake. So this is the location of that magnitude 5.8 earthquake. This is the largest in Oklahoma, is the largest recorded. I think there's paleological evidence for paleostratigraphic evidence for maybe a larger earthquake. So they stepped down their injection and shut in 67 wells in the surrounding area to in an attempt to address this issue. But there's always some lag time, and the events, the two possible solutions here for the fault plane solutions are a west northwest or an east northeast trending strike slip faults. This would be the west northwest would be a left lateral. The north northeast would be right lateral. So, and of course there are several faults, and we'll take a look at that as we go. But the red dots are 2015, so these are the events that have occurred recently. So we go back in time prior to 2010. Not too much going on up in here. Some scattered seismicity earlier on. This is just the kind of damage that, this, I think you could go up there and push that over with your finger. When you get a 5.8 magnitude event, watch out. People can get hurt. People can get killed. We've got sand blows here. We've got liquefaction features and so on in the region. So it has a regional impact. Now this is a pretty busy map. This comes from Walsh and Zobak's 2015 paper, Oklahoma's recent earthquakes and saltwater disposal. And let's just pause for a minute and kind of explain what we're seeing here. The historic seismicity, which we just kind of pointed out on the previous diagram, these yellow dots in the background, they're probably overshadowed. I'm sure there are some in this region, but very, very scattered throughout the state. So it's historically been a region of fairly low levels of seismicity. Hydraulic communication of saltwater disposal with potentially active or critically stressed faults is interpreted as the main cause of these events, and the areas of increased seismicity are shown here in the red dots. The crosses are saltwater disposal wells, so we can see an association between the region of increased seismicity and the distribution of saltwater disposal wells, not one-to-one, which, and it does make it difficult to determine, okay, we've got an event here. Was that produced by injection in this well, this well, this well? Maybe the wells in the region. There is significant enhanced injection associated with enhanced oil recovery operations, these black X's that you see down here. But in these areas, you don't see too much of an increase in seismicity. You just have, you're recycling. You're basically pumping stuff into an interval from which you've removed fluids. So it's kind of a net zero sum. Now this is just another example which shows some of the fault plane solutions and comes from this paper. Again, I've just kind of pulled out the world stress map here. SH max is oriented roughly east-west here, and so most likely we're dealing with right lateral or left lateral strike slip on some of these smaller faults that are oriented, might be critically stressed in relation to this orientation of SH max. And of course there is some variability, but we do see these kinds of faults with an orientation at a low angle to SH max scattered through the area. So most likely these are left lateral strike slip events, as you can see down here on this particular fault in particular. So just looking at the recent activity, I mean, just it tends to go on about every day. One earthquake in the past 10 hours, 10 past 7 days, 90 past 30 days, 1,360 in the past 365 days. So still a busy place in terms of seismic activity, much busier than the historical period, where you would have maybe one magnitude 3 event a year. You know, now you're having several hundred. So this is an example of another area where there is a significant seismicity associated with wastewater disposal. This is in the Youngstown, Ohio area. And there were 109 earthquakes in the range of 0.4 to 3.9 that were detected during about a 14-month period, 12-month, or 13-month, 14-month period in Youngstown, Ohio. About 12 of these were large enough to get, they were recorded by the regional seismic network. A lot of the others were identified by kind of a wavelet matching approach. And of the larger events, they were, well, first of all, I should mention that the injection was between about 2,500 and 2,800 meters here in open hole base of the well. It was cemented down to about 2,500 feet, and then injection was into the Knox Formation and the Mount Simon Formation, which both have about 10% porosity in this area. So the injection effectively was basically right into the crystalline basement. The seismicity that we see here occurred along 2 faults. They started out near the well, and the events then began to migrate westward from the well. So these are after relocation. These are before relocation. This again indicates kind of a left lateral strike slip movement along a roughly east-west fault. So again, induced seismicity observed on these 2 faults. This is your disposal well, and these faults are located almost a good, kilometer to a kilometer and a half below the injection well. So most likely, the fluids that were injected into the well were able to work their way into the fault systems that you see here, down through fractures in the crystalline basement, allowing these what must have been almost critically stressed faults to fail. So this would be the typical scenario that you run into when you're working with saltwater disposal. Is the danger is to reactivate critically stressed faults in the basement. Now we're taking a look at events that are associated with hydraulic or can be attributed to hydraulic fracture stimulation. And so we're just going to come back to this next time. And these cases are fairly limited and not very common, but they do happen. So we'll take a look at this next time, and thanks for joining us.